So my topic, the obesity crisis, what drives dyslipidemia. In this presentation, I'm trying to paint the background for the rest of the day, because I think the background is really what is behind this crisis, and it's a privilege, therefore, to be the first speaker over here. So I'm sorry to say, but I will start with very bad news. And the bad news are that the global pandemic of obesity has been developing very rapidly, and it is huge, as shown by the figures in this slide, where the data is derived from this disease burden collaborators, which was published quite recently. And in fact, the data is from 195 countries, and altogether 70 million people were included over here. And it shows the development over the decades. And the bad news is that 2015, there was already 600 million of people were obesity. And in addition, 100 children who were obese. And please note, which may be surprising, that the most rapid changes shown with those two curves, solid for men and broken for women, are in those who belong to the highest SD group, that is socio-demographic index. But of course, the situation will vary quite a lot between different continents and different countries. The bad news also are that 70% of all BMI-related deaths are due to cardiovascular disease. And this really is disaster, because it means very big disease burden, and that we need to face. So the obesity tsunami is likely to be the biggest pandemic in the history of mankind, and that will have really detrimental effects on cardiometabolic health, and that's what we are going to face over here. Please note also that the lines will be similar if we look at the prevalence for type 2 diabetes and non-alcoholic fatty liver disease, which both are rising rapidly together with obesity. And that means that between 60 to 80% of those 6 million adults who are obese, they have also non-alcoholic fatty liver disease. Therefore, I think that we may ask, is liver maybe the worst kind of ectopic fat depot? And why is that? It is that liver is secreting this plethora of different cardiovascular risk factors, as shown over here. And these together, in fact, create a milieu which promotes the cardiovascular risk and outcomes. In my presentation, I will focus, as the topic was telling, the dyslipidemia. And then, of course, the first question is that why hepatic lipid and lipoprotein metabolism are so important. You should recognize that liver is the center for body energy and lipid metabolism, and it has crosstalk with all these other organs, including brain, gut, adipose tissue, muscle, and so on. And therefore, the question really is that what are the mechanisms underlying the dysregulation of lipids and lipoproteins in obesity? And if we understand better this mechanism, then we probably may also identify some new target to reduce and prevent this global residual risk and CVD burden. So the atherosclerotic dyslipidemia is, as you know, very common in obesity and all these other diseases, and it's a cluster of multiple lipid abnormalities, and usually in the clinics, the measurements are plasma triglycerides and then LDL and HDL. But in addition to the elevation of these triglyceride-rich lipoproteins, there's also accumulation of remnant particles, accumulation of small dense LDL, and then lowering of HDL cholesterol and changes in HDL quality. And recently, of course, we need to include increases of ApoB100 and ApoC3 in this cluster. So I'm trying to highlight what are truly the underlying mechanism for this atherogenic dyslipidemia. First, we should realize that the dysregulation of this triglyceride-rich lipoprotein metabolism is due to two key points, that is production and clearance. And if there is any change in these two components, then the balance in the seesaw will be missed, and this will be reflected also in other components like small dense LDL and HDL cholesterol, and of course remnants, which will be discussed after me. So of course we cannot do anything with genetics, but we definitely can do, and we should do, a lot with the environment, and that means the lifestyle and the metabolic conditions over there. One key problem is that when we consider the mechanism, so if we measure just the concentration, that gives only a static measurements and provides in fact no information about this mechanism which are underlying the concentration, and that means secretion and catabolism and also transfer of the particles and lipids between the different particles. So we need kinetic studies and use of stable isotopes to understand the pathophysiology of this lipoprotein metabolism. And unfortunately, the kinetic studies are very cumbersome, as you know, time-consuming, and also expensive, as there are several steps, as highlighted over here: injection of the stable isotope, followed by very frequent blood sampling, then separation of these fractions, and then processing of the fractions to measure the enrichment in gas chromatography spectrometry, and then finally mathematical modeling using different and complicated multi-compartment models, as some of you know very well. So it means that these studies cannot be done at population level because it's just practically impossible. So the first question really to answer is that what forces are driving the production of these large VLDL particles? And remember, there are two major classes of VLDL particles: the large VLDL particles called VLDL1 and then smaller VLDL2. This slide shows data from a study that we published already a few years ago, where we looked at the kinetics in two groups of obese men. One group had normal triglyceride levels, and the other one had elevated plasma triglycerides. And please note, those guys also had increased liver fat content measured by magnetic resonance imaging. The key point is that there seems to be a stepwise increase in the VLDL1 production rate when we move from the lean controls to those who are obese and have elevation of plasma triglycerides. And the production rate was markedly increased in that group. Please note also that the fractional catabolic rate was reduced in this obese group with high TG level. This slide highlights, in fact, data from multi-center kinetic studies where several of the investigators are sitting in this group, and this was done in Dijon, Gothenburg, Helsinki, and Perth. And it included at that time the biggest group of subjects for kinetic studies, and this had abdominal obesity and additional cardiometabolic risk factor. And this slide particularly focuses on the synthesis pathway. And there's 2 points over here. First, liver fat content quantitative by MRI was close predictor of VLDL1 secretion rate. On top of that, and not surprisingly, also fat mass was a strong predictor for the secretion rate. And that is not surprise, because we all know that adipose tissue is the tissue which releases free fatty acid for hepatic uptake from the circulation. So the message from this part of the study is that liver fat and fat mass seems to be the driving forces for VLDL1 particle overproduction and release. When we looked at the multiple regression model, then liver fat remained independent correlate for the VLDL production, as shown over here. And in addition to that, there was also blood glucose that was another factor. Please note that we included in this model several other factors which correlate with the VLDL production in univariate analysis, but over here in the multiple model, they were not independent correlates. So it really seems to be that hepatic overproduction of the VLDL1 particles is the driving force for hepatic triglyceride accumulation, and also this is driven by the hyperglycemia. We may ask why or what glucose is doing over here. This slide highlights, in fact, the sources for lipids in the liver. There are three major sources: de novo lipogenesis, circulating free fatty acids, and dietary fat. And of course, the circulating free fatty acids are the major source in normal subjects in fasting state. And in fact, the contribution of de novo lipogenesis is limited, and therefore it has been more or less neglected component in the lipid metabolism. However, recent data indicates that de novo lipogenesis may become important. It is markedly increased in fatty liver, also in obesity, as well as also in postprandial state. So we should neglect de novo lipogenesis and the mechanism behind it. When we published that data, so we also recently looked at this paper by Fabrini and Samuel Klein. They published a few years ago, where they looked at how weight gain modifies, in fact, the key metabolic pathways in hepatic lipid metabolism, and they particularly measured VLDL ApoB secretion, which was increased like in our study, and then they also measured de novo lipogenesis, and this weight gain due to the hypercaloric diet increased de novo lipogenesis. But at the same time, as you may note, beta hydroxybutyrate was reduced, and that is a good estimate of lipid oxidation in circulation. And so these two processes, in fact, promote not only VLDL production, but also the accumulation of liver fat. When we consider the regulation of de novo lipogenesis, it should be recognized that it is the key partners are several transcription factors: carbohydrate response element binding protein, sterol response element binding protein, and LXR. And please note that nutrients are regulating these. So glucose is regulating carbohydrate response element binding protein, insulin, TREP, and then we have LXR, which is regulated by sterol recombinant binding protein 2. And LXR by itself can modify both TREP and carbohydrate element binding protein, as well as the activation for enzymes for de novo lipogenesis. So the machinery is complex, but it's clear that the coordinated actions of these three transcription factors are needed to induce hepatic lipogenesis. And so to understand better this mechanism, we ask a question that can maybe excess fructose modulate liver lipid metabolism? And this was done in a multi-center study again, which was done in Sweden, Finland, Italy, and Quebec City. And over there we had 71 middle-aged abdominally obese men who completed the study, and we served 75 grams of fructose as beverages. That means lemonades, 3 bottles per day. Were happy to a diet of 12 weeks. And the diet was very well controlled because they got all the food which they were eating frozen, and the dietitian was following them the whole time. Here we have all those profiles of the metabolic indexes that were measured, and indeed there was several the cardiovascular risk factors which were elevated. So what happened during the study? The aim was to assess the effects of fructose on liver fat, as well as de novo lipogenesis, cardiometabolic risk factors, and also we have done the kinetic data, but we are still analyzing that data, so I cannot share that with you. So this slide shows you the effects of fructose on these multiple metabolic risk factors in these abdominally obese men. And there was, as expected, changes in most of the obesity indexes and also insulin-resistant associated indexes, increase of fasting triglycerides. Please note, increases of ApoC3 as well as FGF21 and quite significant reduction of beta-hydroxybutyrate, indicating reduction of lipid oxidation. This is important because when we consider this de novo lipogenesis, we should recognize that it generates malonyl coenzyme A, and that inhibits CPT1. And if we have lack of CPT1, that impairs importation of long chain fatty acids into the mitochondria and hence beta oxidation. So when the stimulation of glycogenesis by our lifestyle and diet, that also suppresses the lipid oxidation, and these both two processes then favors accumulation of fat in the liver. And the only way for the fat to get out from the liver is to pack that in VLDL particles and export those. Otherwise, there will be really fatty liver. So in this particular study, we measured the beta-hydroxybutyrate changes and DNL changes, and we did see a very nice inverse correlation supporting this concept. When we looked at the different fat depots in this study, as said, there was increase of liver fat, and in fact, the relative increase of the liver fat during this fructose feeding was 10%, and this was less than what was seen, for example, in the weight or in waist circumference, where there was only 1% relative increase, and the same also for the weight. So it was more specific increase in the liver fat. To consider this issue, the next question, of course, is that does this increased synthesis of VLDL particles explain everything? I can already now answer and say no. And the answer is based again on this data coming from the same multicenter kinetic studies. And in addition, that there was a correlation with the secretion rate, there was highly significant inverse correlation between the fractional catabolic rate and plasma TG. So the concentration of plasma triglyceride-rich lipoproteins is dependent on two mechanisms, both secretion of the particles as well as the catabolic rates. As I already pointed out in this previous study with these two groups of obese men, there was a big reduction of fractional catabolic rate in the obese group with high TG. And we looked at also in these groups ApoC3 concentrations, and as seen, it was markedly increased in this obese high TG group. And again, there seemed to be stepwise increase. And when we looked at the fractional catabolic rate, so there was very strong inverse correlation between ApoC3, indicating the important role of ApoC3 in the catabolism. And this slide now summarizes to you the dysregulation of the VLDL1 metabolism in obese subjects. So we have the secretion pathway, which we discussed already. Then again, also in this study, we looked at the clearance pathway, and there was similar inverse correlation between ApoC3 and VLDL fractional catabolic rate, which predicted the plasma TG concentration. And please note the very strong correlation between plasma ApoC3 and plasma TG. So we can conclude that hypertriglyceridemia is really caused by dual metabolic defects, increased secretion, and impaired clearance. And when we looked at the variation, so we were surprised that only 20% of the variation was explained by the secretion pathway, but 50% by the catabolic pathway, highlighting that the catabolic pathway is the most important one and the factors which regulate that one. And as said, ApoC3 is important over there. This means long residence time of this remnant in the circulation, and that will be reflected in the formation of small dense LDL, as well as also the lowering of plasma HDL. So these are consequences about this VLDL dysregulation. ApoC3 comes out here as a very important regulator, and it should be kept in mind, and that will be highlighted by the next speakers, that it has both direct and indirect atherogenic action. And it's not only the inhibition of lipoprotein lipase in the lipolytic process which is due to ApoC3, but ApoC3 also seems to impair the removal of these remnant particles from the circulation to the liver. So this, of course, raises the question that what do we know about ApoC3 metabolism by itself? And therefore, we have recently carried out a kinetic study of ApoC3 in type 2 diabetic subjects to look at this using, again, stable isotope and then the proteomics to measure the enrichment of ApoC3, leucine in ApoC3. So I will just share some of the preliminary data over there. Because, as said, ApoC3 is a multi-phased protein that exerts strong atherogenic function through both direct and indirect mechanism. So this slide shows you the biomarkers of glycemic control in these two groups of subjects, both included 10 men, and the diabetics were treated with metformin. And we intentionally tried to recruit type 2 diabetic patients who do not have very severe plasma triglyceride levels, and therefore there's no difference in the mean levels over here. Despite similar age, body weight, and waist circumference, this type 2 diabetic group had markedly increased in liver fat content, measured again by MRI, and as shown over here. We also observed really robust increase in de novo lipogenesis in these type 2 diabetics. In fact, de novo lipogenesis was increased almost by 40%. But please note, no change in beta-hydroxybutyrate, so no changes in lipid oxidation. The next slide summarizes the kinetic parameters for ApoC3 in these two groups. And we observed highly significant increase of the ApoC3 secretion rate as shown over here. And to our surprise, also the fractional catabolic rate of ApoC3 was increased. And this explains why there was no significant increases in the mean values of the ApoC3. When we looked at the correlations between the parameters, so ApoC3 secretion rate was very strongly correlated to ApoC3 plasma level, and similar correlation was also found for plasma triglycerides. But there was no correlation between ApoC3 concentration in plasma and ApoC3 fractional catabolic rate. So message over here is that secretion rate of ApoC3 is the major determinant of plasma ApoC3 levels. And overall, when we used once again some modeling, so ApoC3 and ApoC3 secretion, in fact, explained 80% of the variation in plasma triglycerides in these two cohorts together. So to summarize, I think that the regulation of ApoC3 is very important, and this slide summarizes the regulation of hepatic ApoC3 secretion by nutrients and different metabolic factors and other factors, including PPARs. And please note that glucose and insulin seems to have opposite effects mediated by different transcription factors on ApoC3 expression. And then, as known, PPAR agonists like fenofibrate do reduce ApoC3 concentration. So I think that this data is very important for the content of this whole meeting. So I would like to say that the data suggests that ApoC3 genes is a promising therapeutic target to reduce the residual risk. And I would like to close out by giving all the thanks to my long-standing international collaborators. Many of you are here, and it's a pleasure to see you here, and especially Professor Jan Boren from Gothenburg, because without Jan and his team, none of our studies would have been possible. So I really appreciate his contribution and long-standing friendship. Thank you.